All right, welcome back. Welcome back. This is a video about resonance, overtones, wave interference, basically all the different ways that we shape our color and our sound and our tone, and then of course applications for our singing. I will be getting into all sorts of different physics concepts in this video. Nothing that you have to you don't have to know any math really, except for maybe like what positives and negatives are. But I think you should be able to track what's going on here pretty well, even if you're not a physics expert. Okay, I have found all these things to be really helpful for learning how to sing. Really, it's like how to create blend. Is when we're talking about blend, it's not some magical thing. It has to do with the physics of the sound in the room. Okay, so quickly though, reviewing. All right, this is from our last video about physics of sound. Sound is vibrations. Okay, we measure the height, the amplitude. Okay, that's measured in decibels, and our amplitude. Our frequency, which is how many vibrations we have per second, is the pitch. Low pitches are a lower frequency. High pitches are a higher frequency or a faster frequency. When we say higher or faster, what we mean by faster is that is more vibrations per second, but the frequency measurement in hertz is a higher number. So we say a high frequency. Really, what we're talking about is like a faster frequency. Okay, but that's why we say high, fast, all that stuff. All right. What else do you remember? Vocal folds create vibrations. The vocal folds vibrate against each other to create pitch. Your muscles, we've got our heavy muscle and our light muscle wrapping around behind. The heavy muscle, remember, stretches itself, or it squishes it pulls, and it makes your vocal folds shorter. The light muscle stretches your vocal folds longer. Okay, and that was this experiment, remember, right? So we have this rubber band. When it's longer, get higher pitches. As we go down, we get lower pitches. Okay, that's how your vocal folds are working. Okay, but I'm going to throw you for a loop here. When you are singing a note or hearing a note, you are actually hearing multiple pitches within each note. Crazy, right? When you hear a note, it's not just one note. It's actually multiple notes at the same time, multiple pitches at the same time. We call these overtones. And that is kind of like one of the big concepts of this lesson here. All right, right now it would take 2 volunteers to do rubber band stuff. I'm actually going to do it with the guitar. It's a little bit easier to do. Okay, you don't need to imagine a guitar string because I got one right here. Okay, now when you hear this string vibrating, we're hearing actually multiple notes at the same time. This string is going back and forth super, super, super fast. Okay, you can't, if you ever get up close to a guitar string, you can see it vibrating. But what you can't see is it's actually vibrating at multiple pitches along that string at the same time. Okay. This diagram, it shows kind of how a string is vibrating. If you imagine that in the middle of each of these is it's vibrating back and forth across a point in the middle here. Vibrating back and forth. I feel like I just get my laser pointer. Oh yeah. Okay, so if you imagine like a point right here along this line, okay, and this string is vibrating back and forth. This big one is the pitch that you hear. Okay, so when we play this note, this is the note that we're really thinking is this A. But along that string vibrating is actually 2 other little spots that are vibrating. And there's also a spot where there are 3 things vibrating, and 4, and so on. The string is actually vibrating at multiple points along the string. And each of those is its own pitch. So built within every note that you hear is actually multiple pitches all at the same time. Okay, this kind of blurry, scale is an example of is the list of all the different overtones. that we hear. So when you play a note, now you'll notice that the first note is very low. It's this one. And we'll get into a reason why we would start with a low note to do this example. But you're hearing all these different things. So here, right, this big one vibrating back and forth. This next one, the next one down where it says 1/2, that is half the length of this big one. So therefore it stands to reason that that is 1 octave higher. That is twice, it's double the frequency. If you remember from the last lesson, right, when we go 1 octave higher, if I go from this A, which is 55 hertz, up to this A, or actually that was, sorry, 110 hertz to 220 hertz to 440 hertz, right? When we go up each octave, it's a doubling. So you think of when we cut this in half, it actually doubles the frequency at which these two are vibrating, right? Because it's going to take them twice as many vibrations over the same period of time. So therefore, it goes up an octave. So that first pitch, that low pitch that we're hearing, the C, for example, the C down here, actually has an octave above it built in. And then a fifth above that for this G, and then another one of these octaves, and then an E and a G. All of these pitches are built in to the note that we hear. We call this note that we hear the fundamental. Okay, so whatever the lowest note is, whatever this biggest vibration spot is, that's the fundamental. Above that note, though, within that same pitch that we're hearing, is built an octave above that, and an octave and a fifth, and then the second octave, and then the second octave and a third, second octave and a fifth, and then there's actually a minor seventh in there, and then another octave, and then seconds. You can see they get closer together as we go up higher. We really don't hear these top notes. They get weaker as you go above the fundamental. The fundamental is the loudest note. It has the highest amplitude. Okay, so remember that amplitude is the volume. So that fundamental note is the loudest. And then each overtone above it gets increasingly quiet. Okay, the amplitude goes down for each one. And we'll see an example of that. Actually, maybe we'll switch to that right now. Okay. Okay, I've got an analysis of my voice here. Right, so you can see it's moving as I talk. I'm gonna sing a note. Okay, and you'll see on the far left when I sing is going to be the fundamental. There's also just a bunch of background noise in here, which is why even when I'm quiet, it's all kind of rocky. Okay, so I'm gonna sing a note. Let's do la la. Okay, so there, I froze my my pitches. You can see that my lowest note is pretty big. Now, this one does a little something where it like kind of it equalizes out your overtones a little bit to make it easier to see. But you can see that within that note, this is just our frequency range. Within that one note that I sang, I've got all these other little spikes. And you can see that they get lower as I go, especially once you get above there's the fundamental and the first harmonic. So this is the octave, the fifth, another octave, third, fifth, and then they really start to tail off. Okay, so that is an example, right, of this. There's that octave, the fifth, the octave, and then the third, fifth, and then they start to fall off in terms of energy, is how we might call it. But they're all built into that one note, which is so cool and really kind of blows your mind. Okay, every instrument, including the voice, follows the same overtone series. So this is built into the physics of it. It doesn't really matter what instrument you have. They all have that same overtone series. Unless it's like a sine wave, okay, which is what we were working with last time, they're all going to have the same overtone series. But they sound different. Why do they sound different? Okay. The difference in sound is what we call timbre. Now I know that this word looks like the title of a Kesha song, but it's actually timbre. Okay, it rhymes with amber. It means the color and tone of a sound, the timbre. If you say timbre, people will know what you're talking about, but timbre is like what the, kind of like what those in the know. You know? If you know, you know. All right, here, these are called histograms. Let me zoom in on one of these. All right, here we got the violin. Okay, on the bottom, on our x-axis is the frequency chart. Okay, the different frequencies. On the y-axis is the decibels, so the volume, or AKA the amplitude. Okay, so each of these is like what is they're all playing the same note. Each of these instruments, these are all a graph of a different instrument playing the exact same note. They're all playing A440, which is this one. Okay, and you can see those frequency spikes. There's A440, there's A at 880, then the fifth above that, another octave, third, fifth, oh, and then there's a spike at another higher octave, and then they really tail off. Right, and you can see, so there's the violin, there's the ukulele. Okay, it tails off the overtones, got a lot fewer overtones. There's the piano, really defined spikes on that one. And then the flute, also super defined. And notice down here, there's nothing going on down here on this flute. That's why a flute can have such a pure sound, because there's nothing in the low frequencies, versus a violin, you get, this is like the scratch of the bow, right? Or on the piano, this is the attack of the hammer hitting the string. It's like a thunk at the beginning of this. And on the ukulele, same thing. This is the strike. But on the flute, if you're playing it really well, nothing in the low frequencies. Okay, so these instruments all play the same note, but they all sound different. Okay, so now I would ask the class, ask you, why do they have different overtone profiles? There could be a lot of different reasons. I just went over a few of them, which is that like the way that they're struck, or the attack is different, right? A piano's got a really heavy attack, a thunk. The violin has a scrunch with the string of the bow on the string. The ukulele has a pluck, and the flute has a chiff, is what we call that kind of sound at the beginning. But this person played it really pure, and there was not a lot of chiff at the beginning. Okay, so the way you attack that, the materials it's made out of. A violin is made out of wood. A ukulele is usually made out of wood. Piano's got a bunch of different things going on. A flute's made out of metal. What type of instrument it is? String instrument, wind instrument, percussion instrument. So a lot of different things that can go into what the sound of it is. Now, what makes singing super cool is that your vocal cords are creating these overtones, but you can change the overtones as you play. Imagine that you were playing a violin, and you could change the shape of the violin as you played it. You can't, because they're made of wood. Right? If you try to change the shape of it as you play it, you break it. But a singer can change what we're doing. That's how we talk. Okay, those changes in what we're doing are called formants. You don't really need to memorize that, but they're called formants. We use to change the sound as we make our voices do different things. All right, these are all examples of different vowels sung on the same pitch. But I thought it would be maybe more interesting for me to sing some different pitches, so you get different vowels. All right, so I'll start on an ah. I'll do ah, e, I, o, u. Ah, e, I, o. Now don't get distracted by that big creepy smiley face that's going on there. Okay, so watch this again. I'll do it one more time. Watch as the different as the overtone profile changes while I'm singing. Ah, e, I, o. See that? So you can actually change your overtone profile while you're singing, which I think we all know we can change our vowels, but we don't think about how why do they sound different? That's part of it, is that they change all those overtones. So we hear certain things spiking in different places. Okay, so here's a little summary of the stuff I've gone over so far. Vibrations happen at different frequencies. Each note you hear is actually many different notes. Okay, that's the Overtones series. We can shape our timbre, or our color, in real time. And timbre is the specific tone, color, and resonance of a sound. It's shaped by our overtones. Okay, let's tuck all that aside for a second. Interference. So last time we just talked about one waveform at a time. Okay, one sine wave or whatever kind of wave at a time. But we, in music, don't just have one wave at a time usually. We have multiple. Okay, when we have multiple waves overlapping, we have what's called interference. There's two different types. There's constructive and destructive. Really, though, they're variations on the same thing. Okay, remember from last time I talked about how when you go above the x-axis, if we think of those as positive numbers, and below the x-axis as negative numbers, what happens when you have two waves on top of each other is that they add. Okay, so if you're adding two positive numbers, so let's say that it's this light gray line is one singer and the dark gray line is another singer. That blue line is the result of the two being added together. Okay, or if you add two negative numbers, you get a bigger negative number. If you add a positive number to a negative number, you get something in between. Okay, so let's say that this singer, the gray singer, is doing they're singing like 2, -2, 2, -2, and the dark gray singer is doing like 4, -4. You get a result of 6 and -6. In destructive land, though, you get a result of math. You get a result of of 2 plus -4, so you get a -2, and then a +2, and then a -2. So they cancel each other out. Okay. In fact, you can theoretically have, if you had two singers and their waves were just out of sync with each other, or two sine waves that are perfectly lined up, but they just get out of sync. Okay, it's called being out of phase. They can cancel each other out and you get 0. So you actually could have two notes playing at the same time, or the same note playing at the same time, but they're out of phase and you actually don't hear anything, which is a kind of a mind-blowing thing. Now, it's not, you can't do it with your voice for reasons that we'll get into. But all right, now combine these ideas. Okay, so we got the overtones. Each pitch has multiple notes, and then combine that with the idea of interference. So there's a sound, right? Got our constructive and destructive interference. Remember that every note has multiple notes built into it. Okay, this is a lot of information here. Here's a chord on the left that the choir is singing. We've got our bass, tenor, alto, and soprano. Okay, they're singing a C major chord. And then here are the overtones from the bass note. Okay, you get your octave in a fifth, and your C major chord above that. And here's your overtones from the tenor, your G, and you got a G major chord built on that. Your overtones from the alto, overtones from the soprano. Now notice I'm capping these all. There's a reason why we're capping up there. But if you add not just the pitches that we're hearing, those fundamentals, but also all the overtones, you get this chord at the end. Okay, that is the overall result of everything. So if I'm just singing that, okay, if I'm just singing this chord, I'm also hearing, let's see. We're hearing all of these notes all built into each other. Now that's really pretty, right? That is part of how we can have lots of color in a chord, even if it's just a straight up major chord. Okay. Let's see. There's something else I wanted to get to, but I'll get there eventually. All right. So that's how, though, we can go from, if you think of like adding those things together, right? We've got all these different notes. They have different notes built into them. We have all this interference. That is how you go from a sine wave to something more complex, like this big old mess of waves over here. Okay, you're never going to hear a recording of a choir singing and be able to like just plot it out on a simple sine wave. Another cool thing Oh no, I'll get to that. All right. Applications for singing. So this is where we kind of apply it to what we know already. Unison. Think about, we've got all these complications, right? This is two people singing together. Now imagine that you split it off into 4 different people, right? Or 10 different people, or 20 different people. This is just, imagine everyone's trying to sing the same single note, but you're off by just a little bit. You get all sorts of interference, right? Just from the one pitch. That's like, imagine we're all sine waves, but we're all just slightly out of tune. That's kind of interference you can get with just a few people. Now, we're not just singing sine waves, we're singing overtones as well, right? And we're singing different notes than each other. So look at this chord at the end here. Oops. Yeah, I guess you can't look at it like that. Okay, look at this chord at the end here. Like, think of that, but now everyone's a little sour on the pitches. This is why we really want to work on making sure our pitches match each other. Okay, plus, then you add in the complicating factor of our vowels and the different overtone profiles that our vowels have. So not only do we want to make sure we're matching our pitches, but we also want to make sure we match our overtones, because if I'm on an A vowel and someone else is on an E vowel and our overtones aren't matching, then we're going to hear not only the wrong vowels, but it's just going to sound, the blend is not going to be as good. So when we talk about blend, everybody, like, blend is not some abstract concept. Blend has to do with the physics of how the shape of the sound that we're creating. It's our pitch, it's our timbre, and our timbre helps get created by our placement and our overtones. Now, you have control over your overtones. By changing the placement of the sound, you are amplifying or cutting off different frequencies. Let me demonstrate this here. So I'll do an ah, okay, and I'm going to place it backward to forward. You see how there was movement on those upper overtones? I'll do an E. I'll try to go nasal. So you do all this. You have all this control over what you're doing with your voice to make the different kinds of blends. And using those overtones, by like allowing those low overtones in, that's how opera singers can sound so big. Right? If I try to sing really like whispery, right? If I'll do like one of my fave artists, Phoebe Bridgers, right? If I try to do like a Phoebe Bridgers voice, like la versus la, did you see how much more the overtones got activated when I did that? Right? Like on the Phoebe Bridgers voice, everything is kind of low and reserved, but when I go big, the upper overtones get activated, and that is going to fill up a space. So if you're an opera singer and you're trying to fill up a whole space with no microphone, you use those make big resonant spaces so that you can maximize your overtones. Higher pitches also have fewer overtones. Okay, so I mentioned earlier. Let me scroll back here. This guy, right? I said the overtones from the soprano. I kind of stopped them because we just don't have as much energy in our high overtones as we do in our high notes as we do in our low notes. Okay, so if I sing a high note, E, you can see how those higher notes, right? There are only a little bit of excitement in those higher overtones versus when I do the low ones, we get all this stuff happening. So higher notes just do not have as many overtones, which can make it tricky, right? It means that higher pitches, they can sound more pure, but they can also sound more easily out of tune because the fundamental isn't obscured. When I'm singing low notes, I want my pitch to be on, but to be totally honest, it doesn't need to be quite as accurate because I don't have as much. There's a lot of stuff that can kind of obscure the sound, but those higher notes can sound more out of tune because you can't hide behind any of those overtones. And lower pitches sound fuller because they've got more weight behind them. Okay, that's why a lot of people like to sing in their chest voice, because it's just got a little more oomph to it. I wrote, you have the power. It's you who controls your tone, your resonance, and your timbre. Okay, everybody has to work together, but everybody has to be thinking about their own pitches in order to make things work. So when you're up there, it's not just about hitting the right notes. Okay, that's not it. When we sing well or sing in a choir, we're also thinking about our vowels, our placement, because that's really what we're responding to when we hear something. We're hearing the pitch, yes, but we're really hearing the color and the tone, and you have all this control over it. You just have to experiment and find out. One last thing that I thought was cool that I didn't cover. If you notice, sorry for all the slide flipping through here. Where's the one I'm looking? This one. Okay. These notes, C, C, E, C, E, G. This is the Overtones series, right? This is for C. If you look right here, what you were building when you're playing any note, the Overtones series is going to create a major triad. Okay, for any note. It's built into the physics of the thing. Okay, so every note, every string vibrating has a major chord built into the sound. So when we wonder, well, who decided that a major chord was going to be the foundation of our harmonic theory? Like, who made that up? Nobody made it up. It's built into the thing that we're hearing. Okay, so that major triad is the basis of our harmonic foundation, because it's built into the string vibrating itself, which is, I just think, so cool that a major triad is like built into whatever we hear as far as like a music instrument or a voice singing. So that sums it up. Okay, basically it's like it's all physics. There's no magic to it. Okay, I mean, it can be a magical experience. The experience you have can be, it can't be maybe defined with physics, but what we do is physics. We are playing with sound and science in order to make our voices work. So be thinking about these as you're in rehearsal and you're singing by yourself, all this different stuff. And that is it for today. I'm excited to keep working with this material. I'll see you later. Bye.